To Dr. Tarter, I asked her if she was part of that generation of female scientists who faced some difficulties. And she said, yes, I did. You had to take home economics instead of shop. If you took calculus, you were thought to be kind of unusual. But she said her father particularly encouraged her to pursue and convinced her that she could do anything. And so we all have her father to thank for that. She was raised in New York. She attended Cornell University with a full scholarship from Procter & Gamble Incorporated, and she got a Bachelor's of Engineering and Physics degree with distinction. She began graduate work in theoretical physics at Cornell, but she interrupted her study to begin a family, something important to all of us, relocated in California, and changed her field of interest and earned a PhD in astronomy from the University of California at Berkeley. As a graduate student, she became involved in the search for radio signals for extraterrestrial civilizations using the Hat Creek Observatory 85-foot telescope. And she said once she got interested in that, there was no question she found as interesting to investigate. She'll tell you about that investigation, I'm sure, with all the energy and passion that she brings to that. She says she has the best job in the world. And as anyone who thinks they have the best job, she's done very well. She's received a Lifetime Achievement Award for her contribution to the field of exobiology, and in particular, the search for extraterrestrial intelligence. Dr. Tarter is married. She has one daughter and 3 stepdaughters. She's written dozens of technical articles. She's lectured extensively. She's also done research on more conventional astrophysical topics and given numerous presentations. She belongs to professional societies. She serves on all kinds of advisory committees. But when her daughter was asked to fill out what her mother's occupation was, she said she looks for little green men. So let's welcome the scientist who looks for little green men.
Okay, now we find that the computer has not gone to sleep. That's a good sign. And I need to get plugged in. All right, now I can take this opportunity to say thank you so much for inviting me to come to Portland and share my passion, and some would say obsession, with the search for extraterrestrial intelligence. And I hope when you leave tonight, you will have a better feeling for the distinction between the science fiction and the science fact of the search for extraterrestrial intelligence. Let's start with a little bit of focusing about who we are and where we live. All right? We live in an enormous expanding universe. It's expanding more rapidly all the time. And within that observable universe, we find hundreds of billions of galaxies. We live in one called the Milky Way. And within those hundreds of billions of galaxies, we find in each one hundreds of billions of stars. But if we're interested in the question of are we alone, are there any other sentient, intelligent creatures sharing our universe, it's not just 10 to the 22 stars that we need to focus on, but we need to think about where life and intelligent life can evolve. And at least in terms of life as we know it, that is, biology like us, somewhat like us, planets are important, right? Life as we know it is a planetary phenomena. That means not only that we evolved on a planet that had a profound effect on life, but that life in itself had a profound effect on the planet. So planets, not just stars, are of interest. And the question is, how many planets are out there? All right, until the end of the previous millennia, we knew only of the 9 planets in our own solar system, and we're very fond of that little pale blue marble. But since 1995, we have been discovering planets circling nearby stars. And to date, there are, 75 planets known to orbit stars other than our own sun. And in 7 cases, we have found systems with more than one planet, true planetary systems. Now, none of those planetary systems to date are very much like our own. Here we have Mercury, Venus, the Earth, and Mars, terrestrial inner rocky planets of our solar system. And here in the Upsilon Andromeda system, we have 3 planets, all of which are bigger than Jupiter, and the 2 of these are in orbits very much shorter than the Earth's, and this is an orbit that's very much shorter than Jupiter. So what are these big planets doing in where we expected to find little rocky planets like ours? Well, that was a surprise. It turns out it's an instrumental bias. The instrumentation on the telescopes finds best massive planets in short period orbits. So guess what? That's what we found first. And we believe that there are probably other planetary systems with planets like Jupiter at a distance out here 5 times the distance of the Earth to the Sun. So 5 astronomical units way out here, we expect to be finding in other solar systems, other planetary systems, analogs of Jupiter. The problem is that it takes a full orbital period to be able to infer the presence of these planets, none of which we've seen, by the way. All of the methods that we've used to date have been indirect. And we haven't had our precision equipment on the telescopes long enough yet to find average old Jupiter-type planets at 5 astronomical units from their stars. But keep your eyes and ears open, because that's going to be coming within this decade. The instruments will have been on the telescopes long enough. We will either be beginning to find true solar system analogs, or we'll be learning something rather unexpected, that is, that something is very unique about our own solar system. Now, in all cases, the instrumentation is incapable of finding anything much less massive than the planet Uranus. So planets like our own Earth, good planets, are very hard to find. They're small and they're dim and they're difficult to find. We expect that when we can do the job, we will find that such planets are plentiful and that there are billions within our own galaxy. But we don't yet know that. And it's going to take a new methodology to find terrestrial planets. We're not going to be able to use the radial velocity or astrometric techniques that we've used so far, which basically record the fact that as you have a planet circling a star, it tugs just a little bit on the star, and the star moves towards you and away from you or side to side just a little bit, because the planet's so much smaller than the star. What we'll need to do to find terrestrial, Earth-like planets is stare at the star and notice that if there's an appropriate orientation, and if the planet like the Earth goes between the star and our telescopes, that as it goes in front of the star, it will dim, it will block out a little bit of the star's light. Now, if Jupiter does this, you lose about 1% of the star's light, and that's pretty easy to see. There's even a possibility that we could do those kinds of observations from the ground. But when a planet like the Earth goes in front of its star, or the sun, a sun-like star, it only blocks out 1 part in 100,000 of the light. Here's the correct picture for that. That big red planet is Jupiter. That's Uranus. That little black dot is the Earth. And that's the sun. And you can see that an Earth going in front of the sun is not going to block out very much light at all. But we have just now developed precision CCD arrays, which when we put them in a spacecraft to get above the fluctuations in the Earth's atmosphere, should be able to find the first evidence of terrestrial-type planets. It's a mission called Kepler. It's expected to launch in something like 2006. And for about 4 years, Kepler, the spacecraft, will stare continuously at 100,000 stars. And then that's a large enough number of stars so that if terrestrial planets are fairly common, then you will get enough of a probability to have a good alignment to see transits and to be able to tell us what the statistics are. Not only what percentage of stars have massive Jupiter-like planets in short period orbits, what percentage of the stars have Jupiters at 5 AU, but we'll know what the statistics of stars that actually have terrestrial planets are. So again, within the decade, we'll know a lot more about good places for life, at least life as we know it. Now, on the one place that we do know about, the Earth, life started very quickly. The solar system began to form about 4.5 billion years ago. By something like 4 billion years ago, we had a cooling surface on the planet Earth with liquid water. And by 3.8 billion years ago, we have evidence, chemical evidence in the rocks, in the oldest rocks that we can find on Earth, that life was already there. And we don't know where life got started. We wonder whether, in fact, the energy from lightning in the primitive atmosphere helped to form heavier biological molecules out of the organic precursors that were there. Or perhaps at the edge of the ocean and the land, the tides with their continual hydration and dehydration and rehydration of the shoreline might have driven the chemistry to become more complex. Or even down here at the base of the ocean, where the mantle is splitting apart, getting the upwelling of this very hot, very rich magma. And today we find really wonderful and bizarre colonies of forms of life that don't use sunlight down there. Maybe that's where life got started. We just don't know, and it's a fantastically interesting area of research. Where did life start on Earth? But we do know that it happened quickly, and that encourages us to think that it happened elsewhere as well. In fact, Christian de Duve, who has a Nobel Prize in chemistry, is very fond of saying that life is a cosmic imperative. By that he means that biology is just a lot of complex chemistry, and chemistry is pretty deterministic. So given the same conditions elsewhere, you're going to come up with biology and life. And it sounds really good when he says it, particularly in his very distinguished Belgian accent. But you know, if I were sitting in the audience, I'd be thinking, okay, where's the evidence? And that's what you always have to do. You have to ask, show me. How do you know? Where's the proof? And in the case of the life elsewhere in the universe, we don't yet have the evidence. But we're beginning to look, and look quite hard. We're starting with our own solar system, and what we'd like to do there, both NASA and ESA are planning for future spacecraft missions to return to the planet Mars, to visit Europa and Callisto, these ice-covered, very large moons of the planet Jupiter, to look for life. To look on Mars for fossil evidence of life, or perhaps deep beneath the surface of Mars, there might be some liquid water where we might even today find extant life. The reason that we're interested to do this, and we expect that we might have a positive result, is that 4 billion years ago, when the early Earth was wet and warm, early Mars was also wet and warm. And as life was getting started on Mars, on the Earth, it might have started on Mars. And we're particularly interested in that because in 1996 there was a rather fantastic announcement. A claim was made that a potato-sized rock, which had been found on the Antarctic ice sheets in 1984, was actually a piece of Mars that had been chipped off that planet a very long time ago by a collision, had wandered in space for a while, and then been captured by the gravitational field of the Earth and fallen to the Antarctic ice sheet, where it lay and was kept well preserved. Now, that's pretty impressive, and we know that that's a piece of Mars by analyzing the trapped gases in that rock. But there was something more spectacular that was claimed in 1996, which was when they looked at structures that they found in this meteorite, this Martian meteorite, there were structures that certain researchers claimed actually were fossils of very small life, microscopic life. And that was an incredible claim, and it stirred up a large bit of controversy in the scientific field that hasn't been settled today. It is not yet clear whether what is being seen in that Martian meteorite is mineralogy or biology. But indeed, it was so exciting, and it served to remind scientists that early in the solar system's history, the terrestrial planets were not biologically isolated. Indeed, if life started on one of them, it might have hitched a ride buried deep inside a rock onto another of the planets. And so life as we know it today, in fact, could be due to Mars. We might all be Martians. It's a possibility. I'm not saying that it's correct, but it is one of the questions that's being asked. So when we go looking for life elsewhere in the solar system, we not only have to ask, is it there, but we have to ask, is it us? Or is it some independent evolution of biology? Those are two different questions, and both very important. We want to go back, we want to go to Callisto and to Europa and see if indeed beneath this icy crust there are liquid water oceans, and if there's been water there for 4.5 billion years, 4 billion years, perhaps indeed there's even life there. And if we find life beneath the ice, we'll have actually a pretty good case that that isn't us, that isn't our biology, that it's an independent evolution. So number 2 in this field, finding a second independent origin of life within the solar system, would do a great deal to supporting Christian Dedoux's claim that life is a cosmic imperative. If we find 2 examples in one solar system, we'll be a lot more confident that life indeed is ubiquitous throughout the universe. Well, what about life beyond our solar system? Again, NASA and ESA are both working on very, very ambitious programs to try and image terrestrial planets around nearby stars. That's a very difficult job. I wasn't kidding with that slide that says good planets are hard to find. Right? Imagine that you wanted to see a terrestrial planet in optical light. Here's an analog to show you how difficult it is. Suppose you take one of those huge spotlights that illuminate football stadiums, and you put a firefly right on the rim of that spotlight. Now you go a couple of miles away, and you try and look back and see that firefly. Hugely difficult task. There's that big, bright floodlight right there, and your eye does not spatially resolve where the firefly is from where the floodlight is. And that's the problem with looking for a terrestrial planet. The planet doesn't emit light of its own, it simply reflects light from the star. And it's at optical wavelengths, the reflected light from the planet is 1 billion times fainter than the light from the star. And as far as our telescopes can tell, they're right in the same place. Now, if you work at infrared wavelengths, it's a little better. The contrast ratio is only 1,000,000 to 1. That means that the planet is only 1,000,000 times fainter than the star. And that's where we're going to try and work about 20 years from now. Hopefully we can orbit free-flying telescopes that work in the infrared and work together, combine the light from these telescopes together as an interferometer. And this is an artist's concept of the US mission called the Terrestrial Planet Finder, and this is the European mission called Darwin. And before very long, I think these two are going to become one, because it's a huge technical challenge and very, very expensive, and everybody is interested in this question. So what we hope to be able to do is fly this little constellation of telescopes and combine the light from the telescopes in such a way that it nulls out, it removes the light from the central star. It takes that light right at the center from the star and spreads it all around the edge of the field of view of the telescope. And in doing that, we may get the starlight to be down at such a low level that now you have a chance to find those terrestrial planets that might be there close to the star. It won't be, home movie kind of things. We won't be looking at the waterfront real estate on these planets. We'll be lucky to get a single pixel image, but it'll be the first time that we've seen a pale blue dot other than our own. And that's an enormous challenge, and scientists are working very hard to be able to do this, probably 2 decades in the future. And if we can do that, okay, we'll try something even more amazing, harder, and more informative. What we'll try and do is see if we can do a chemical assay of any atmosphere that that planet might have. And what does this mean? Remember, the starlight is coming from the star. It passes through the planet's atmosphere. It bounces off the planet's surface. It was reflected back out through the atmosphere and comes to our telescopes. And in the process of going through the atmosphere, if there are certain atoms and molecules in the atmosphere in sufficient quantity, they can absorb light from the star at certain frequencies. What they do is they put a spectral fingerprint on the light from the star. And the different atomic species and molecular species have very specific fingerprints. It's just like humans. Every molecule is different from every other molecule and in terms of its spectral signature. And if we stare for enough days at one of these single pixel images of a terrestrial planet, perhaps we can see the fact that there is some exotic chemistry going on in the atmosphere, just as there is in the Earth's atmosphere if you looked at the Earth from a large distance. If you looked at the Earth and compared its atmosphere with the atmospheres of all the other planets in our solar system, you'd find some really peculiar stuff. In the Earth's atmosphere, you'd see molecular oxygen and methane. Now, why is that so amazing? Because if you have those two gases in a laboratory, they will instantly combine and become carbon dioxide and water vapor. That's the equilibrium configuration. But in our atmosphere, we have coexisting, very non-equilibrium chemistry. We have the oxygen, we have the methane. They're recombining all the time to give carbon dioxide and water, but at the base of our atmosphere, on the surface of the planet, we have a very rich biological source of those gases. We have the plants, which are doing photosynthesis and producing oxygen, and we have the termites living in the guts of many, many creatures producing methane gas. And we even have a bunch of cows out in the pasture, and bovine flatulence is adding to the methane content. So it's cows. It's all about the cows. That's what our Earth's atmosphere looks like. And it looks like no other in the solar system. What we'd love to be able to do with one of these terrestrial planets that may be circling nearby stars is to find the same sort of thing. Well, that chemical assay is a bit beyond our even current projections of what we think we can do in 20 years. But what we may be able to do is find the chemical evidence of ozone and then weave a complicated story that would lead us to believe that there was some life there. And that will be a fabulous announcement, should that be forthcoming in the next decade or two. And everyone will be very, very excited, and there will be follow-on missions to do a better job and to learn more. But the one thing that you're not going to know from looking at the atmospheric chemistry, and you can deduce that there's biology there, but you're not going to know whether that biology is microbes or mathematicians. And it's really the mathematicians for which we have a particular bias. When we ask this question, are we alone, we're interested, but not so interested in whether we share the universe with other algae and pond scum and microbes. We really are thinking about others like us. We just have this bias. And so we want to expand that search to know about intelligent life. And there's somebody else that's interested in intelligent life. Hollywood's been making a pretty good living on that question for a while now. Whole bunch of blockbuster movies that Hollywood does, and most of the time they just get it totally wrong. As some of you, I'm sure, are aware, there was one movie, Contact, which got it mostly right. However, nobody wears headphones in the SETI project. Nah. Not even my blind colleague who is portrayed in the movie, Kent Cullors. And it is Kent, a blind physicist, Kent's been blind since birth, brilliant, who has taught all of our computers the silicon intelligence that we use to find the signals, because the data rates are so huge and so vast that no carbon-based intelligence, with earphones or not, can do the job. It's the computers that are listening. Couple of other slight problems with the movie. You may remember the first kiss scene here. Well, you know, from a scientist's point of view, this is a little embarrassing because Jodie Foster takes 10 to the 11, the number of stars in the